Okay, so that's an example of text type. So now let's go on and do a few things. The first thing we'll do is look at some thermodynamic relations. And we start with something that we already have, the first law, that delta Q is equal to delta W plus du. We are assuming that delta Ke and Pe are negligible. Now let's look at what delta W actually comprises of. And this includes work done at the system boundary, that if there was a cylinder piston arrangement, there was a piston over there, and the system pushes this, so the system boundary moves up over there and just adjacent to the piston, then that little movement it did, if pressure during that time was infinitesimally small changed, then this was P multiplied by the volume change, and the way it comes about is that the distance that it went through was dl, area is A, and the force is P into A, so PAdl is the work done, AdL is the volume change. So this is one type of work, but this could be any other types of work also that include by stretching. So there's a tensile strength multiplied by the length, stretching of a rubber band or something, or a surface tension work where there is surface tension into the increase in area, or you could have electric charge going through an electric field. All of that get added up. And for this particular round, we say that, look, if these things are all negligible, then we have a substance here which is a simple compressible substance. Okay, and now we say, what did the second law tell us? It said that for a reversible process, ds is del q by t, or del q is equal to TdS. So now we combine these two, put delta Q from here into this as PdV, and we'll write in terms of specific properties, because now we got only properties in this equation remaining. So we get TdS is equal to du plus PdV. This is one relation we will use, and since it involved only properties, there is no restriction on where it is used, where it is not used. The second property we'll get is by the definition of enthalpy. The specific enthalpy is specific internal energy plus PV, and if we open it up in elemental form, dH is equal to du plus PdV plus VdP. And we say that if you look at it here, this is du plus PdV, and in this equation also we got here du plus PdV. So we can substitute that, and we get the next equation we are looking for, that TdS is equal to, this term goes to the other side, and this becomes dH minus VdP. So this is the second of the equations that are of interest to us. Okay, so we just keep that in mind, that later on also when we come to the next module and we look at properties, we will start exploiting all of them. Let's now look at one special case. And see how we can start applying what we have learned. And the simplest case we will take is that there is, say, a flow And in this we make a system. We say that, okay, this is the system that we have. There is one inflow, there is one outflow. So this we will call as 1, this is 2. And we say this is the simplest system and I want to analyze this. And we say, okay, conservation of mass. For this system, there is one inflow, there is one outflow. So this becomes, or I will just keep it as I and E. M dot E minus M dot I plus d dt mCV equal to 0. The first thing before we can even do this is to tell us what type of a system is this. This is an open system. What type of a treatment shall we apply to this? A controlled volume treatment. And so this equation came. If it were a controlled mass, this equation would not have been there. Now we start making a series of assumptions and say my first, let's say assume, and this is purely our own judgment. We can assume something, we need not assume something. One, steady state, which means that d dt of everything, whatever, is 0. So if once we do that, this equation simplifies and we get m dot E is equal to m dot I, and this we can say is in generically just m dot. So this is what we got from the conservation of mass. And remember, every system has to obey conservation of mass, conservation of energy, and the second law. So now we go to the second one, conservation of energy, which is the first law equation, and for a control volume. And here we will get that long equation. So let's put that down together. Q dot CV plus there is only one inflow. So this becomes m dot from this equation into HE HI plus VI square upon 2 plus GZI. This is equal to W dot CV plus m dot into HE plus VE square by 2 plus GZE plus rate of change of energy in the control volume. So coming from the most general equation that we have derived, that summation sign is gone because there is only one inflow, one outflow, and instead of m dot E and m dot I, since there is only one inflow outflow, this m dot has come over here. And since we assume steady state, what it means is that this term is 0. And now we say, well, since the fluid is just flowing there, and if there is no, this is the next assumption we make, Q dot CV equal to 0, that means there is no heat transfer with the surroundings, it is not being heated, it is not being cooled, it's just flowing. If Q dot CV is 0 and W dot CV is also 0, that means we are not doing any work on it. There is no pump or any piston or something else going on into it. So we assume that these two are also 0, then this term goes off, this term goes off, and we are left with a simple term. Now then m dot will also cancel out on both sides, and what we are left with HI plus VI square upon 2 plus GZI is equal to HE plus VE square upon 2 plus GZE. So that's the simplest thing that the conservation of energy told us, in which we also invoke conservation of mass. Now we go to the second law. And so, well, this is an open system. So what do I get? And it tells us that for the open system, that equation that I have just written there, this will come in. This long equation comes in, where now this is 0, steady state, no heat transfer, this is 0, and we are left with these two terms, so which is m dot Si minus m dot Se is equal to S dot generation. So we have 0 is equal to MISI minus m dot ESE plus S dot generation. Well, we don't know what is S dot generation, so it doesn't help us too much. And this is where we will exploit one of the equations we just wrote a few minutes back. And it is that TdS is equal to dH minus VdP. So we'll write that one. And say, can I simplify it further? And say, look, we already assumed that Q dot Cv is 0. Now let's also assume that this system is internally reversible. It is reversible, it does not exchange heat, so this process is reversible adiabatic. And we had seen yesterday that if that is the case, then ds is 0, basically says that Si is equal to Se. So with that assumption, we are now left with 0 equal to dH minus VdP, or dH is equal to VdP. And now let's integrate this and say, well, if I have to do an integration on this one, dH will be H2 minus H1, but this will be integral VdP 1 to 2. So if we know the relationship between V and T, we can solve it. But we'll make another assumption to make life easy and say that V is constant. That means the fluid is incompressible. That being the case, this integration then helps us, and it becomes H2, which will put He minus Hi. This is equal to V integral 1 to 2 dP, which is V P2 minus P1. And we can now, P2 is PE, P1 is PI. And now we put this back into this equation, and what you get is V times Pi plus Vi square by 2 plus GZI is equal to VPE plus VE square by 2 plus GZE. And to make it look a little familiar, we will just write V. We know this is 1 upon density by rho. So this becomes Pi plus rho V square by Vi square by 2 plus rho GZI is equal to PE plus rho VE square upon 2 plus rho GZE. Or by looking at it, it tells us that P plus rho V square upon 2 plus GZ, this is constant. And that's an equation you probably came across in school, which is your Bernoulli's equation. This may come up in fluid mechanics, where you derive it in a slightly different way, but that's how the equation came. The thing is, we made so many assumptions. And listed out, we said this is in steady state. Then we said Q dot Cv equal to 0. W dot CV is equal to 0. And then we said it is reversible, no irreversibilities. And the last one we said V is constant in compressible fluid. So Bernoulli's equation is applicable only when all of these are satisfied. Any one of these is violated, we cannot apply Bernoulli's equation. So what looks so simple, and we have used it so many times, has a very good number of restrictions before you can even use it. Okay, so just wanted to show this, how we can take a very simple system in which there is no work transfer, no heat transfer, do an analysis applying all the three conservation equations and come up with a relation which can be used quite generally. Okay. So before I proceed, there are some questions. Okay, the question is, what is entropy of real gases? Yes, module 3, we will come to the point of how do you calculate entropy of real gases and all types of things. Okay. There is a question here, what is the difference between open system and closed system? So I refer you back to the first module where we spent time on this, but very quickly, an open system is one where there is mass inflow or outflow across the system boundary. A closed system is one where there could be energy inflow or outflow, but no mass inflow or outflow. And the third question is, what is a Rankine cycle? I haven't yet come to that. We have only talked about the Carnot cycle. After looking at the properties of a substance, when we look in the last module at applications, we will look at Rankine cycle in quite a bit of detail. So it is basically a modification of the Carnot cycle using steam, which is practicable. So that's very quickly, that's what it is. But the thermodynamic details of it, we will take it up in the last module.